All right, so, for a philosopher like you, I gotta imagine this tension between, like, deterministic physical laws and the kind of free, boundless world of thought. That's gotta be, like, a really interesting area, right?
Oh, absolutely. It's a fundamental question, isn't it? How can these two seemingly disparate realms coexist?
Totally. And today we're diving deep into this debate, all sparked by a thought experiment that, honestly, it sounds deceptively simple when you first hear it.
Yes, the deceptively simple thought experiments. Those are always the most intriguing, aren't they? The ones that seem to unravel entire universes with just a few carefully chosen words.
Yeah, exactly. And the one we're tackling today is the infamous Maxwell's demon. Picture this. You've got a container, completely insulated, filled with gas.
All right, I'm picturing it.
Okay, now divide that container right down the middle with a partition. But here's the catch. This partition has a tiny little hole in it.
A hole, so small a molecule could squeeze through.
Exactly. Now imagine that hole we have this demon. Not a scary demon, more like a mischievous little imp.
I like where this is going.
And this demon, it has this incredible ability. It can see and know the speed of every single gas molecule that comes near that hole.
So it's like a microscopic traffic cop
Hmm.
directing the molecules.
In a way, yeah. But here's the thing. It's not just watching. This demon has a tiny little shutter it can open and close over that hole.
Okay, I see where this is headed. It's going to start sorting those molecules, isn't it?
Exactly. It lets the fast-moving molecules through to one side and the slow-moving ones to the other. What's the result?
Well, you'd end up with one side of the container getting hotter because of all the fast-moving, high-energy molecules.
Right, and the other side gets colder. But here's the kicker. The demon itself isn't doing any work, not in the traditional sense. It's just using its knowledge.
That's the mind-blowing part. It appears to be violating the second law of thermodynamics. That law says entropy, or disorder, always increases in a closed system.
But our demon, by sorting hot and cold, seems to be decreasing entropy, creating order out of chaos,
Hmm?
seemingly for free.
So how can something that seems so logically possible, even plausible on a small scale, so blatantly contradict one of our most fundamental physical laws? It's a question that has puzzled physicists and philosophers for over a century.
And that's what we're going to explore in this deep dive. Why can't this demon, despite its cleverness, actually exist and break the second law?
I'm all ears. It's not every day you get to delve into the mind of a demon, even a hypothetical one.
So today we'll be tracing the history of this debate from the very first time Maxwell cooked up this little thought experiment all the way to modern interpretations involving information theory and the limits of computation.
It's fascinating to see how the problem has been reframed over time, shifting from this idea of a physical demon to more abstract concepts of information and knowledge.
We've got some real heavy hitters joining us on this journey. Maxwell himself, of course. Then Marian von Smoluchowski, who tried to explain why a physical demon wouldn't work. Leo Szilard, who brought in this crucial idea of information having a thermodynamic cost. Rolf Landauer, who linked thermodynamics to the process of computation. And finally, Charles Bennett, who refined our understanding of the unavoidable price of messing with information.
A real intellectual all-star team, and each one offering a different piece of the puzzle, a different way of looking at this seemingly simple problem.
So our mission today, and I think this will really resonate with you as a philosopher, is to understand the arguments against Maxwell's demon. Why can't it create a perpetual motion machine? And what does this tell us about the relationship between the physical world, the information we acquire, and these seemingly fundamental laws of nature?
I'm eager to delve in. It touches on some really deep questions. The role of observation, the limits of knowledge, and the nature of reality itself.
Yeah, it really does. So let's start at the beginning. Maxwell himself. He was trying to understand heat in terms of atoms and molecules.
Right. Unlike some of his colleagues who wanted to derive entropy increase directly from the movements of those particles, Maxwell saw something else. He understood that if thermodynamics arises from the statistics of these countless particles, well, then the second law might not be an absolute unbreakable rule.
So you're saying he thought it might be more like a really, really strong tendency based on probability rather than a hard and fast law.
Exactly. Think of it like this. The second law might be true for crowds of molecules, but not necessarily for every single one, every single time. Maxwell wasn't just questioning a law, he was highlighting a gap in our understanding based on the limits of what we can observe.
I see. So he's already working with a probabilistic mindset. Now, can you walk us through that standard temperature demon scenario he envisioned?
Of course. Let's revisit that insulated container we talked about. It's filled with gas, right down the middle with that partition and the little hole. Now, the gas inside is in thermal equilibrium, meaning the temperature is uniform throughout.
But the molecules themselves aren't all moving at the same speed, are they?
Not at all. They're zipping around with a whole range of speeds, but it's their average kinetic energy, the energy of motion, that determines the temperature.
And then our little demon enters the picture, sitting there by the hole, watching those molecules come and go.
With its incredible ability to know the speed of each molecule as it approaches the hole. Now, if a molecule is moving faster than average and heading towards, say, the right side of the container, the demon swiftly shuts the door, bouncing it back.
It's like a bouncer at a very exclusive molecular club. You fast molecule, you're in. You slowpoke, you're out of here.
Precisely. And for molecules coming from the right, it does the opposite. It blocks the slow ones and lets the fast ones through to the left.
So what happens as this demon keeps up its selective sorting?
Well, you start to get a buildup of faster molecules on one side and slower ones on the other. Remember, temperature is just a measure of average kinetic energy.
So the side with the faster molecules gets hotter, and the side with the slower ones gets colder.
Exactly. And here's where the second law starts to sweat a bit. Because the demon, by creating this temperature difference, seems to be decreasing entropy. And it's doing it without doing any work itself.
It's just opening and closing a tiny door, no energy expended, at least not in the way we normally think about it.
Right. The demon acts as a kind of intelligent filter. It's using information to direct the flow of energy. And this resulting temperature difference, you could theoretically use it to power a heat engine and extract useful work.
That's the kicker. You'd be converting heat into work without any energy input. That's a big no-no according to the second law. It's like getting a free lunch in the universe, and the universe does not give out free lunches.
Precisely. It would be like creating order from chaos without paying the energetic price. Now, you also mentioned a simpler pressure demon. How does that one work?
Oh yeah, the pressure demon. Think of it like a one-way valve. It blocks molecules coming from one direction, but lets them pass freely from the other.
So it's not about speed anymore, just direction.
Exactly.
Yeah.
It's even less sophisticated than the temperature demon. But the result is similar. You get a buildup of molecules on one side, creating a pressure difference.
And again, this pressure difference could be used to do work, seemingly violating the second law once more.
So to be clear, Maxwell wasn't saying the second law was flat out wrong. He was suggesting that our macroscopic view, our inability to mess with individual molecules, that's what makes the law seem so absolute.
Right. He saw the demon as a thought experiment, a way of highlighting the limits of our perception. The second law holds true at our level because we're dealing with gazillions of molecules. We can't control them one by one. But maybe, just maybe, if we can manipulate individual molecules, we could exploit those tiny fluctuations, those deviations from the average, to our advantage.
So he threw down the gauntlet, challenging our understanding of thermodynamics. And then Smoluchowski steps in and says, hold on a minute. Let's see if a physical demon could actually pull this off.
Exactly. Smoluchowski wanted to ground the demon in reality, in the laws of physics. He imagined replacing that clever little imp with a tiny spring-loaded trapdoor.
A physical mechanism. That makes sense.
And this highlights a crucial point. If you're trying to cheat thermodynamics with a purely passive device, well, thermodynamics is likely to bite back. The machine becomes part of the system it's trying to exploit.
So this trapdoor, how's it supposed to work?
The idea is that a molecule hitting it from one side, a fast-moving molecule, could push the door open and pass through.
Because it has enough momentum to overcome the spring.
Right. But a molecule hitting from the other side would be less likely to open the door even if it were moving fast, because it's working against the spring. It seems like you could create a pressure difference that way, right?
It makes sense at first glance. But Smoluchowski saw the flaw. It's all about thermal fluctuations.
Exactly. That spring and trapdoor, they're not isolated. They're in constant contact with those gas molecules, getting bombarded all the time.
So they're absorbing energy, heating up.
Precisely. The spring starts to jiggle and vibrate. The trapdoor flaps open and closed randomly. Any sorting effect it might have had is completely lost.
It's no longer this clever, discriminating gatekeeper. It's just another part of the chaotic system.
And that's Smoluchowski's point. A purely mechanical demon, operating under the same thermodynamic constraints as the gas itself, can't reliably and continuously violate the second law.
No free lunch, even at the microscopic level. Unless, maybe, you bring intelligence into the picture.
That's the loophole Smoluchowski left open. He couldn't entirely rule out the possibility that an intelligent being, something capable of purposeful action and observation, might find a way around this modified second law.
Which brings us to Leo Szilard, who said, okay, let's talk about intelligent demons and the role of information. And he came up with this incredibly elegant thought experiment involving just a single molecule.
Yes, Szilard took the whole demon scenario and stripped it down to its bare essentials. A single molecule in a box.
Talk about simplicity. No more swarms of molecules.
It's exactly just one molecule bouncing around. And the box is connected to a heat bath, so it stays at a constant temperature. Now imagine you slide a partition into the box, dividing it in half.
So now our lonely molecule is trapped on one side or the other.
Right. But here's the crucial part. If you know which side the molecule is on, you can use that information to do work.
Oh.
Imagine attaching that partition to a tiny weight. If you know the molecule's on the left, let's say, you can let it push the partition to the right, lifting the weight.
Because you know which way the pressure, tiny as it is, will act.
Precisely. You've extracted work from the system just by knowing where the molecule is. And the energy for that work, it comes from the heat bath. The molecule stays at the same temperature throughout.
But wait a minute, that still sounds like a violation of the second law. We're getting work from heat with no other input.
That's precisely the puzzle Szilard presented. And his key insight was this. The apparent violation hinges on the act of knowing, of measuring where the molecule is.
So information itself becomes a player in the thermodynamic game.
Exactly. It's no longer just about energy and entropy. Szilard argued that this knowledge, this information, must have a thermodynamic cost. Acquiring it must somehow increase entropy somewhere else in the system.
It's as if information itself has a weight, an energy price tag attached to it. You can't just get it for free.
And this is where the debate starts to get really interesting, because it raises a whole new set of questions. What is the cost of information? How is it paid? Where does the entropy increase happen?
So Szilard opened up this whole new avenue of exploration, linking information and thermodynamics. Now, Rolf Landauer comes along and says, let's talk about the physics of computation itself.
Landauer was a visionary. He looked at the very act of computing and asked whether there were fundamental thermodynamic limits, regardless of the physical hardware you use.
So he's not talking about specific computers, but about the underlying principles of how we process information.
Exactly. And at the time, there was this idea that getting even a single bit of information had a minimum energy cost. But Landauer challenged that. He drew a distinction between logically reversible and irreversible operations.
What's the difference?
Think of it this way. A reversible operation is like flipping a switch. You can always go back to the original state. You haven't lost any information.
Like a not-T gate. If the output is 1, the input was 0. No information lost.
Precisely. But an irreversible operation is like mixing two colors of paint. You can't unmix them. You've lost information about the original colors.
Like an A and D gate. If the output is 0, you don't know which inputs created it. There are multiple possibilities.
Exactly. And Landauer argued that these irreversible operations, the ones where you lose information, those are the ones that have a fundamental thermodynamic cost.
Because you're essentially compressing the possible states of the system. You're reducing the number of options, the number of ways things can be arranged.
And that reduction in possibilities, that's what leads to an increase in entropy in the environment. It manifests as heat dissipation. He really zeroed in on this idea of resetting a bit.
So like forcing a bit to be 0, regardless of its previous state.
Right. And to do that, you need to do work. Imagine that single molecule in the box again. If you want to make sure it's on the left side, representing a 0, you might have to compress it, push it over there.
Which requires energy. Energy that gets dissipated as heat.
Exactly. Landauer calculated that the minimum energy needed to reset one bit is kT-ln2, a fundamental limit. And that energy, it has to go somewhere. It ends up as heat in the environment.
So he's saying that computation, the act of processing information, is not just some abstract thing. It's a physical process with real-world thermodynamic consequences.
That was his radical proposition. Computation, in its essence, is about manipulating physical systems. And those manipulations are bound by the laws of physics, including thermodynamics.
So Landauer sets the stage. And then Charles Bennett enters the scene and says, hang on, let's revisit this idea of measurement. Can it be reversible?
Bennett's contribution was crucial. He realized that logical irreversibility wasn't strictly necessary for computation. You could simulate irreversible operations with reversible ones, even though you might need to store extra information temporarily. And this had huge implications for the demon.
Because the demon's main job is to observe, to measure the speed of those molecules.
Exactly. And Bennett argued that measurement itself could be logically reversible. Imagine the demon measuring the molecule's position, storing that information in its memory.
So now there's a correlation between the molecule's position and the demon's memory state.
Right. But this correlation, it can be created without any loss of information, without any increase in entropy.
So the demon isn't breaking the second law just by looking.
Not according to Bennett. But here's where Landauer's principle comes back into play. Bennett argued that to complete a cycle, to be ready to measure the next molecule, the demon has to clear its memory. It has to forget what it just saw.
Uh-huh. And that act of forgetting, of erasing information, that's where the thermodynamic cost comes in.
Exactly. Erasure is irreversible. You're reducing the number of possible states, just like Landauer described. And that requires energy. Energy that gets dissipated as heat, neatly compensating for the work the demon extracted earlier.
So the demon's not violating the second law by being clever or by observing. It's violating the law by having a bad memory.
It's a brilliant resolution. It ties the whole thing together beautifully. But of course, not everyone was entirely satisfied with this information-theoretic exorcism of the demon.
Right. We have Ehrman and Norton who raised this sound versus profound dilemma about these explanations. What's that all about?
They argued that many attempts to resolve the paradox fall into one of two traps, the sound horn and the profound horn.
Intriguing names. What's the sound horn all about?
It's the approach where you essentially take the second law for granted. You assume it's true, and then you argue that something must be happening to prevent the demon from breaking it.
So you're using the law itself to justify the existence of a cost that upholds the law.
Exactly. Schulard's argument that measurement must have an entropy cost falls into this category. And some interpretations of Landauer's principle do as well. But the problem is, it feels a bit circular.
Like you're assuming the conclusion you're trying to prove.
Exactly. And you don't necessarily get a deep explanation for why the demon can't function. You just show that assuming a cost is consistent with the second law.
So what about the profound horn? What's that one all about?
That's where you take Landauer's principle or some other principle linking information in thermodynamics and you say, this is a fundamental law of nature independent of the second law.
So it's not derived from statistical mechanics, but stands on its own.
Exactly. And from this new fundamental principle, you can then potentially derive a modified second law that inherently excludes demons.
But what are the issues with that approach?
It implies that our current understanding of statistical mechanics is incomplete. It suggests that without this extra principle, demons would be possible. And if we don't have strong independent reasons to believe in Landauer's principle as a fundamental law, how can we be sure some other clever demon couldn't get around it too?
It raises some deep questions about the foundations of physics and the status of information itself. Is it a fundamental ingredient in reality, or just a way we describe things?
That's a question that's still very much up for debate. Now, our sources also mention some alternative perspectives, some attempts to create engines without demons.
Engines that exploit those microscopic fluctuations without any intelligent intervention.
Exactly. The idea being that the second law might only be strictly true for macroscopic systems. Maybe at the level of single molecules, there's more wiggle room. But the counterargument is that to make these engines work reliably, you still need to reset them.
And that resetting process, even without a demon, is likely to incur a thermodynamic cost, consistent with Landauer's principle.
Right. And then we have Wojciech-Zurek, who brought in this fascinating concept of algorithmic complexity.
Algorithmic complexity. That sounds pretty intense.
It is. It's a measure of how compressible a piece of information is. Zurek imagined a demon that could store lots of information about the molecule's movements without erasing its memory.
So it's trying to be super efficient with its memory storage.
Exactly. But Zurek showed that even if the demon is really good at compressing that information, the average cost of eventually resetting that memory still comes out to that KT-ln2 limit.
So no matter how clever the demon is, it can't escape that fundamental cost in the long run.
It seems so. And then there's the perspective that demons do exist, at least in a limited sense.
They exist how?
These arguments focus on the idea that Boltzmann entropy can actually decrease in certain situations, like when you insert that partition in Szilard's engine.
Right. The molecule ends up on one side, effectively reducing the entropy.
And you can extract work from that lower entropy state even without a demon. But to make it a repeatable cycle, you still have to reset the system.
And that resetting will likely generate heat, making sure the second law isn't truly violated in the end. And of course, we can't forget about quantum theory, which always throws a wrench into things.
Oh, yes, the quantum realm, where things get really weird. It introduces all sorts of new complexities to the idea of measurement and entropy. Zurich tried to interpret Szilard's engine in terms of quantum superposition and wave function collapse.
So the act of measurement itself becomes a quantum event.
Exactly. But it's not a clean, straightforward interpretation. There are still a lot of questions. And it seems like finding quantum versions of Landauer's principle is much more challenging.
So the quantum implications for the demon are still an open area of research. But zooming back out, it seems like the whole idea of what the demon is and what the exorcism is trying to achieve, that's all shifted over time.
It has. Maxwell was just pointing out that the second law might not be absolute. Then Smoluchowski tried to constrain the demon with a modified law. But as we learned more about information and computation, the goal became to prove the demon impossible altogether.
And the concept of intelligence became less about some magical being and more about the physical processes of information handling, measuring, storing, erasing.
Exactly. And this raises a really interesting philosophical question. Is information itself a fundamental part of reality, or is it just a way we describe physical correlations?
So is it like an ingredient in the universe with its own energy cost, or is it just a label we use?
That's a big question, and I don't think we have a definitive answer. Bennett's resolution, for example, relies on seeing the demon as a physical system with a memory. It's bound by the same laws as everything else.
So it's not some magical being exempt from physics.
Right. But if that's the case, then maybe information itself isn't this fundamental thing. Maybe it's just a convenient way to talk about those physical correlations, those relationships between different parts of the universe.
So in the end, what's the big takeaway for the philosopher listening to this?
Well, I think the Maxwell's demon debate highlights how connected seemingly different areas of knowledge are. Thermodynamics, information theory, computation, they all come together in this fascinating puzzle.
And it forces us to think about the limits of what we can know and do. What are the fundamental laws of the universe, and how do they constrain us, even at the smallest scales?
And if information does have a fundamental thermodynamic cost, that has huge implications for how we understand reality itself. It suggests the much deeper connection between the abstract world of information and the concrete world of physics than we might have imagined.
Absolutely. So yeah, the original demon, the one that could just break the second law without consequence, that one's probably not possible. We can't get a free lunch in the universe.
It seems that way, though the universe does surprise us sometimes.
True enough. But here's something for everyone to ponder, something to keep you thinking even after this deep dive is over. If we have to erase information to avoid violating the second law, does that mean there's a deeper arrow of time at play? A directionality tied to the act of forgetting?
Now that's a question I'll be pondering for a while.
Me too. Could forgetting be just as fundamental to the universe as the tendency towards disorder? It's a question for physicists and philosophers alike. We hope this deep dive has sparked your curiosity and given you some new tools for thinking about this age-old puzzle.
It's been a fascinating journey. Maxwell's demon might be a hypothetical creature, but the questions it raises are very real, and they'll continue to intrigue us for a long time to come.
And on that note, we'll leave you to your philosophical musings. Until next time.
Until next time.